In this presentation, I will be explaining the basic characteristics of operational amplifier. Coming to the operational amplifier characteristics, operational amplifier input side is a differential amplifier as we have shown here. There are two transistors with the NPN transistors with whose bases are the input 1 and input 2 here, and the outputs are measured from the collectors, respective collectors output 1 and output 2, and RC1 and RC2 are the collector resistors, both are equal, and these are having the same characteristics, and here plus VCC and minus VV to RA. Therefore, this is the op-amp input side circuit diagram. And here, looking front to this one, there are different characteristics of this op-amp. One we call it as input bias current. Second we call it as input offset voltage. Then input offset current. These are all the input side. And output side, output offset voltage. Therefore, these are the four characteristics of DC characteristics of operational amplifier. That will be specified in the manual. These values will be specified. Let us see what do you mean by first input bias current. Input bias current, there are two, as I told you, there are two transistors at the input side with the Q1 and Q2. And here, if IB1 and IB2 are the base currents drawn from the DC source, so is the from the DC source, bias current actually it is equal to not base current, it is the bias current. It is the let IB1 and IB2 are the bias currents drawn from the DC source as biasing currents. The input bias current is defined as the average of the input DC base currents, or this IB1 and IB2 are the base current which is used as a bias currents, which is represented as a bias currents, IB1 and IB2, and this IB1 is the base current which is represented as the bias currents of the Q1 and IB2 of this Q2 bit. And this average of these values, IB1 plus IB2 divided by 2, that we call it as input bias current. And here IB1 plus IB2 divided by, this is the input bias current, IB bias. And here example, if IB1 equal to 85 microamperes and IB2 equal to 75 microamperes, the input bias current, that is equal to I in bias, that is equal to the average of these two, 85 plus 75 microamperes divided by 2, or 80 microamperes is the input bias current. Because though there we are taking of the transistor of having the same characteristics, there will be a slight deviation in this characteristics, and because of that one, IB1 may not be equal to the IB2, and the average value of this IB1 and IB2, that is IB1 plus IB2 divided by 2, that is taken as input bias current. Next one is the output offset voltage. Output offset voltage means that, as again this is a circuit diagram at the input side of an op-amp, and here assume that we are grounding both inputs. Here input 1 as well as input 2, you are grounding, that is as shown here. Ideally speaking, the output voltage should be equal to 0. But in practical case, even though you are shorting the input side to the ground, you are grounding the input terminal to the ground, there will be an output voltage, and that voltage we call it as output offset voltage. Therefore, because of the difference in electrical characteristics of these transistors Q1 and Q2, this of transistors of this one, VBE1 will not be equal to VBE2. That is, base to emitter voltage VBE1 will not be equal to VBE2. Normally it will be some 0.6 or 0.7, something like that. That may not be equal that for these two transistors, and because of the difference in VB1 and VB2, due to this one, the output voltage of the op-amp will not be 0 even if the inputs are grounded, even though you are grounding the inputs 1 and input 2, like this one, plus terminal as well as plus terminal, and this is a non-inverting terminal and inverting terminal. You are grounding that one. Even though you are grounding that one, output voltage will not be equal to 0. And this voltage is called, how much is this voltage you are getting at the output even when the inputs are grounded, that we call it as output offset voltage. That is because of the difference in VBE1 and difference in base to emitter voltage. Even though the characteristics are of the same characteristics, but there is a slight difference in VB1 and VB2 that will be causing an output voltage even when the inputs are grounded. That voltage we call it as output offset voltage of operation amplifier. Now the input offset voltage, as we have seen in the previous slide, even when the inputs are grounded, output is not equal to 0. Therefore, in order to make the output voltage equal to 0, you may have to apply certain voltage at the input side. Then only will be output voltage equal to 0. That voltage we call it as input offset voltage. Therefore, the output voltage will not be 0 even if both inputs are grounded, that we have seen in the previous slide. And we have to apply a small voltage, that is we have to apply a small voltage V in at the input terminal to make the output voltage to 0 voltage. To make the output voltage, you have to apply certain voltage at the input side. And this voltage V in is called the input offset voltage. Only when you are applying an input offset voltage of V in, the output will become equal to 0. Therefore, thus the input offset voltage is the voltage required to be applied at the input for making the output voltage to 0 voltage. The voltage that is to be applied at the input side in order to make the output voltage equal to 0, that we call it as input offset voltage. That is given input offset voltage. That is in this. That is actually this input offset voltage that is equal to, we have seen the previously, output offset voltage. That voltage divided by the gain of the amplifier, that is equal to the input of voltage that is to be applied. That is called the input offset voltage. The next parameter is the input offset current. Input offset current. Input offset current means that, again coming to this the circuit diagram at the input side of an operation amplifier, two transistors Q1 and Q2 here. Since the input of the transistor cannot be made identical, that is IP1 cannot be equal to IP2. IP1 you cannot make IP2. The input offset current is that input offset current that is given as IP1. The difference in this base current, that is called the input offset current. IP1 minus IP2, never that will be equal to, ideally though it is equal, but practically IP1 will not be equal to IP2. And how much is the difference in base IP1 and IP2, that we call it as input offset current. Typical offset current of a BJT op amp is around 200 nanoamperes. That is, this much current is the difference in IP1 and IP2. And that for an FET based op amp, it is equal to 10 nanoamperes. Or if it is a bipolar junction transistor base, it is equal to more 200 nanoamperes. But if it is instead of this BJT, if you are using FET, can also be used. In that case, the input offset current is very less, 10 nanoamperes only. For the voltage due to the bias current, that is IP1 minus IP2 into the this one, this resistance RC, and where this RF, that's the feedback resistance RF, and that is the voltage due to this bias current, and where RF is the feedback resistance. So because of this difference in bias current that is flowing through the feedback resistance, there will be a voltage that is equal to IP1 minus IP2 into RF, where RF is the feedback resistance. Anyway, input offset current is the difference in current of IB1 and IB2, and that will be causing a voltage drop when it is flowing through a feedback resistance RF. That is the input offset current. Another parameters of operational amplifier. So the other characteristics of operational amplifier. There's another character is an AC characteristics of a very important characteristics of operational amplifier. That is what we call it as slew rate of an op amp. This is very important. And slew rate is the maximum rate of change of the output voltage in response to the step change. When you are giving a step change input here, output is changing. It takes certain time to reach that output. And the maximum rate of change of output voltage in response to a step change in input voltage, that is what we call it as slew rate, and unit is equal to volts per microsecond. Unit is equal to volts that per microseconds. And as an example, for assume that here 0.5 volt per microsecond, that is the slew rate, 0.5 micros per microseconds. In this case,
Assume that there is a change in voltage of 20 volt. That is that the voltage is changing from minus 10 volt to the plus 10 volt. The voltage is changing from minus 10 volt to the 10 volt plus 10 volt. That is a change in voltage equal to 20 volt. If slew rate is equal to 0.5 per microsecond, meaning that for to change from minus 10 to 10 plus 10, that is 20 volt change, it requires that much microseconds, or it is equal to 20 divided by 0.5, or 40 microsecond is required to change from minus 10 volt to plus 10. Even though the input is changing suddenly from minus 10 to plus 10, output is not reflecting that one. It takes certain time to change from minus 10 to plus 10, and that time is decided by the slew rate. If the slew rate equal to 0.5 volt per microsecond, in order to change from minus 10 to plus 10, that is 20 volt change, it requires 20 divided by 0.5. 40 microsecond is required. This is a 40 microsecond is required from minus 10 to plus 10. And slew rate, that is a slew rate of an operation amplifier. And slew rate gives an idea how quickly a given op amp responds to the change in input voltage, or the slew rate, how quickly the op amp is responding to a change in input voltage. That is represented by this slew rate of an operation amplifier. Another thing is that slew rate is related to the frequency response also. That is, for an IC741 that's widely using in the laboratories, IC741, the slew rate equal to 0.5 volt per microsecond. Per microsecond, the output is changing 0.5 volt. That is the meaning. Per microsecond, the output voltage can be changed 0.5 volt. Therefore, output from the amplifier can change by 0.5 volt for every microsecond. That is the meaning of slew rate of 0.5 volt per microsecond. That is a slew rate of IC741. And the maximum operating frequency of op amp, that is a function of the slew rate. How much frequency it can operate, a operation amplifier can be operated. The maximum frequency of operation F banks, that is equal to whatever the slew rate, that divided by 2 pi into V peak. This is a V peak, means the peak value of the output voltage. V peak means peak output voltage. 2 pi V peak. Slew rate divided by 2 pi V peak is the maximum frequency of operation of a operation amplifier. For op amp, the frequency response of an op amp is a function of this, or it's a function of the slew rate. And as slew rate changes, the maximum frequency that can be operated will be changing. Anyway, the maximum frequency of operation of an op amp, F max, is given by slew rate divided by 2 pi into V peak, where VPK is the peak value of the output voltage. Just to show the significance of slew rate of an op amp in the maximum frequency that can be used, a problem is given in which the amplifier shown in the figure, that is an op amp amplifier, it is a inverting amplifier in which the feedback resistance RF, input resistance R1, and the load resistance RL. And here it is used to amplify an input signal whose peak output voltage is equal to 100 millivolt. Output peak value voltage is equal to 100 millivolt. What is the maximum operating frequency of the amplifier? How much frequency this can be operated? That is decided by the slew rate of the op amp. Slew rate of the op amp for a IC741, you can get from a manual. IC741, the slew rate is equal to 0.5 volt per microsecond. Per microsecond, it can change 0.5 volt. Therefore, here, in order, the V peak equal to 100 millivolt. Therefore, the maximum frequency that it can be operated is given by F max is given by what is the slew rate divided by 2 pi into V peak. Therefore, the slew rate is given as 0.5 volt per microsecond. That divided by 2 pi into V peak is given by 100 millivolt. And substituting here means 100 milliwatt means 0.1 volt. And substituting in this equation, here we will be getting it is equal to 796. It's equal to kilohertz, 796 kilohertz. Therefore, this IC741 with this change in output voltage can be used for a maximum output frequency of 796 kilohertz. Therefore, this maximum frequency for an op amp can be used, that is decided on the slew rate of the device. For an IC741, the slew rate equal to 0.5 volt per microseconds.